Alright guys, so since I'm not here, we're going to do this lesson via video. Please make sure you get the two worksheets from the sub, one called Lesson Chi-Squared Goodness Fit Test, and then Critical Values. So, at the top of your page, it says, so far we have looked at t-tests, which focus on the population mean. Now we'll look at what's called a chi-square goodness fit test, which focuses on the population proportions of relative frequencies. And so the main question becomes, when do I want to use this? When's the purpose? And that's what I'm going to write down over here. So when should Sorry, that's a fancy little X. That's a terrible X. No, that's good enough. It's when we're going to be comparing observed and expected frequencies. So this is usually you're using, like, say we're comparing flipping a coin, and theoretically the probability is 1/2, right? But if you start flipping a coin and you do a bunch of trials, you may not always get a 50-50 split between heads and tails. And so what this is trying to do is, say you know a theoretical probability and you're going to do your own experiment, and you're kind of comparing, does the experiment actually give you the theoretical? And that's kind of what this is trying to do. It's doing something that that has been observed versus what is expected to happen. So that's when you use this type of test. So right here it says, what is the theoretical probability of rolling a 6-sided die? Well, theoretically, there is 6 outcomes, and you should be able to land on 1 out of 6. All right. So let's actually look at how to do one of these chi-square goodness fit tests. This is going to take a couple of slides to kind of get through because I broke it up into little sections for us. So problem one says, suppose Cheyenne rolls a die 60 times and obtains rolls in the table. Since the relative frequency or proportion outcomes are different, Cheyenne claims that her die is biased. All right, so here it says 1, 2, 3, 4, 5, 6. Those are like the different sides of the die. And this is how often that person got those values when they rolled the die. Well, over here, it lets us know how to write a null and alternative hypothesis for this type of test. So our chi-square test, our null hypothesis would be the probability equals whatever the probability of getting, like, say, a 1 on the die. P2 would be like the probability of rolling a 2 on the die, and so on and so on. The alternative hypothesis is written as at least one of those probabilities is not true. And that's how we write our null and alternative hypothesis. Below it says, in general, the population proportions under null hypothesis do not have to have all the same values, which you're going to see in example 2. But for right now, we know that the probability of getting a number on a 6-sided die, the theoretical probability, is 1 out of 6. So we would say the null hypothesis is probability 1 is getting a 1 out of 6. The second probability, so getting a 2 on the die, is 1 out of 6. The probability of getting a 3 on the die is 1 out of 6. Probability of getting a 4 on the die is 1 out of 6. Probability of getting a 5 is 1 out of 6. Probability of getting a 6 is 1 out of 6. All right, and therefore the alternative hypothesis is at least one of P1 does not equal 1 out of 6. P2 does not equal 1 out of 6. P3 does not equal 1 out of 6. P4 does not equal 1 out of 6. And then, P5 does not equal 1 out of 6. So there's our null and alternative hypothesis. All right, and so after you've done that, the next one we would want to do is define what we call the expected frequency, which you'll notice is right here, a little note. Expected frequency is equal to the number of trials times the theoretical probability. So our expected frequency is going to be our 60 rolls, our 60 trials, times our theoretical probability, which is 1 out of 6, which is going to give us 10. That's our expected frequency. Now, you'll see in this little table here, this F and then EXP, that's referring to the expected frequency. So in reality, all this in this table is meant to be 10 for the expected frequency. You can see that we have F of ops, which is referring to the frequency of observed. So this is what they actually got when they did the trials themselves. And then over here in blue, we have the formula that calculates the chi-square value for us. Okay, that's going to calculate the chi-square value for us. Now, for us, we can make things a little easier. Now, unfortunately, I'm not going to be able to show you me typing things into the calculator. So you're going to have to kind of do this on your own. So if we want to calculate all the values that are going to show up in this little table here, what we're going to do, we're going to go to our list and we're going to put the observed frequencies in list 1 and the observed frequencies and the expected frequencies in list 2. Okay, which means if I want to type this all in, you could individually do it right here and just type each number in and do that calculation, or you can let the calculator do it for you. Now, to make that happen, you're going to make this be L3. So you know when you look at the very top of your calculator, it says L1, L2, L3. You want to make sure that your L3 is highlighted. The L3 is highlighted. When it's highlighted, you can type this formula in there. And you're like, well, how am I going to type it in there, Mr. Sika? There's no F observed. Well, your F observed is you'd have parentheses. Well, you'd make a fraction first, parentheses, L1 minus L2 exponents, you have your exponent squared, and then you're going to have it divided by L2. And it will fill this entire chart in for you. Those values are going to be 10, 0, 2.5, 0.4, 0.9, and then 0. Or you can individually calculate them yourself. As an example, to do it by hand, so if you're not getting it to work with the calculator, I'll do that right over here. So let's say I do the first row here. I would have the parentheses 20 minus 10 squared over 10. Well, 20 minus 10 is 10. That's squared over 10. 10 squared is 100 divided by 10, which is 10. And that's why we get a 10 here. Okay. Once again, your calculator can do it for you. Down here where it says total, once we have all those little values, this is the chi-square calc value, and we just add up all these green numbers here, and that's going to give us 13.8. Then it says below, make a decision on whether to reject our null hypothesis on the chi-square calc value. We need to calculate a p-value and compare it to the significance level test. All right, so let's think back for a moment. All right, so remember we've been doing some t-test, right? And when we had a t-test, hence the name, it had a curve that looked like a normal distribution, but its mean was at 0, and then like we could have, t over here, we could have like a negative t over here. Well, chi-square kind of works in the same way, except its curve looks like this down here. It's not a normal distribution curve. But that chi-square value, think of it kind of like that t value that you always find, and then you're looking for that p value, that area underneath the curve. It's just the difference is the curve is a different kind of curve than the t value. So the curves are different, but you're doing the exact same thing. So just to kind of read over this sentence here, in the goodness fit test, if the null hypothesis was not true, then the difference between the observed frequencies and the expected frequencies would be large. Hence, the value of chi-square calc would also be large, so that the chi-square goodness fit test is the probability is equal to the probability to observe a value greater than or equal to chi-square crit. So it's basically trying to say that the area underneath the curve is where the probability is that we are looking for to help us to make a decision if we accept or reject the null hypothesis. So here, let's take a look at how can we do this without the table. Now, I showed you the table way with all that detail. So if this is something you're going to use in your IA, you could show that table, you could show that work, you can use a bunch of that paper. It'll work out really great for you. But if you're trying to do a test, you're going to want to do it this way, okay? So the first thing we're going to do is, once again, you want to go ahead and enter in your data in list 1 and list 2. So your observed frequency is list 1, expected frequency is in list 2. And you're going to go ahead, once you have that in there, you're going to hit stat, test, then the chi-squared GOF test. Now there's two tests that look very similar. Make sure you're picking the one that says GOF. Okay? Now it's going to ask you for the degrees of freedom. Over here you have this whole little speech about the degrees of freedom. It's just reminding you how it works. It's just the categories minus 1. Now for us, we're dealing with a 6-sided die. So we have 6 categories, minus 1 is 5. So our degrees of freedom is going to be 5. Now when you type it in, your p-value should end up being 0.0169. And as you know, I like this as a percentage to help compare significance levels. And so we're going to have 1.69% as the p-value. All right, so once you've done that test, now we have to determine if we're going to accept or fail to reject, or if we're going to reject or fail to reject the null hypothesis. So we're looking at the p-value is less than 5%. Since the p-value is less than 5%, we reject the null hypothesis. It says state a conclusion for the test. Well, we conclude at a 5% significance level that Cheyenne's die is biased. Now that seems weird. You know, we've done something like this before. Last year, we actually went ahead and said, hey, we know theoretically that you can get a 1 out of 6 chance of getting any number on that die. But if, as you look at this person's table, we're kind of rejecting that idea. But why is it being rejected? Because this test says so. But that test only says so because they only did 60 trials. If you want to see real theoretical probability happen in the real world, you have to do hundreds or even thousands of trials. Now, in your calculator, we did a simulation program that did it for us, and it took us, I think it took us around 400 something trials before we started to see that 1 out of 6 theoretical probability show up. So that's why we may have a conclusion that doesn't seem logical to us from what we know, but it happened this way because of the limitations this person put on their experiment. They didn't do enough trials. They simply didn't do enough. All right, let's take a look at problem 2. So the table shows the grades received by university students taking a second-year computer course. In the following semester, a new coordinator is appointed for the course. The new coordinator is concerned by the high number of high distinction awards, and wants to determine if the course should be adjusted. It is considered usual if 5% of the students receive a high distinction, 10% receive distinction, 15% receive a credit, 40% receive pass, and the remaining receive a failing grade. Conduct a chi-square goodness fit test to determine whether the course should be adjusted with a 5% significance level. All right, so first we should state the null and alternative hypothesis. So our null hypothesis is going to say that the probability for P1 is 0.05. And you're probably like, where did you get that number from, Sika? Well, I'm calling this probability, this high distinction over here in this table, P1. And from the story, the high distinction 5% of the people did that. So that's a 5% probability. So that's the 0.05. Well, then I'm going to do P2. Well, P2 is going to be distinction, and that was 10%. So it's going to be 0.1. Then I'm going to have P3, which is going to be credit, which had a 15%, so that's 0.15. And then P4 is going to be the pass, which had a 40%, so that's 0.4. And then probability P5 is going to be the fail, which was a 30%, so 0.3. The alternative hypothesis is going to be at least one of, and then we just kind of list all the different probabilities with the not equal sign. All right, so now we have our null and alternative hypothesis. Now we're going to go ahead and do a chi-square goodness fit test. So we need to create our table that illustrates our observed and our expected frequencies. So I'm going to go over here and make a little table for us. So this is my P1, my P2, P3, P4, P5. This is going to be the frequency of the observed, the frequency of the expected. Now the observed is over here. They show it to us. So 16, 21, 21, 59, 34. Now to get the expected frequency, remember that's the number of trials times the probability. Well, this time it's going to be different every time because we have different probabilities every single time up here. So for the expected frequency, I'm going to, as an example, I'm going to take the total number of trials, which is this 151 we see over here, times the probability. I'm going to do P1 first, which is going to be times 0.05. That's going to give me 7.55. Then I'm going to do it again. I'm going to do 151 times 0.1. That's going to give me 15.5. Once again, I'm doing each individual probability because each one has a different probability. And I'm just going to kind of go through with the rest. So this is one's going to be 22.65. This is going to be 60.4. And this one is going to be 45.3. And once again, I'm going to make this right here L1 and this right here L2. Once those are entered in as my lists, I'm going to go ahead and do stat tests. And then I want to make sure I pick the chi-squared G, sorry, spelling that wrong, GOF test. I'm going to need to know my degrees of freedom. So once again, I have 1, 2, 3, 4, 5 categories. So 5 minus 1 is 4. So degrees of freedom is 4. Just going to let the calculator do the work. And they're going to tell me that the chi-square calc value is 14.7. And it also, using that test, is going to tell me the p-value is 0.00529. As a percentage, we all know that's going to be 0.529%. So now we have to figure out, we're doing a 5% significance level. So we're going to compare 0.529%, that is less than 5%. So we reject the null hypothesis. We conclude at a 5% significance level that The distinctions should be adjusted. Once again, that's how you do a chi-square goodness fit test when the probabilities are all different. So here we have some limitations to chi-squared goodness fit test. So here it is. In order for chi-squared to be distributed appropriately, the sample size n must be sufficiently large. Generally, n is sufficiently large if none of the expected frequencies is less than 5. In cases where the expected frequency is less than 5, we can combine similar categories to get more reliable results. For example, when investigating the number of serious sport injuries by a hospital, the following expected frequencies are calculated. Since the expected frequencies of 2 age groups are less than 5, we combine the categories. So you'll notice here, these were less than 5. And therefore, you notice if you look at the combined table, they just started merging the value, those categories. So they went from 20 all the way to 30 because those were, they just need to be bigger than 5. And so that's what they ended up doing. So if you ever come across something that you need to do that, just remember if your frequency is less than 5, you need to combine them until they are 5. Okay, so the next sheet of paper is called critical values. Now, critical values is an alternative way to use your chi-squared goodness fit test. Instead of finding a p-value, you can use critical value instead. That's essentially what this is trying to tell us. So I'm going to kind of read it. I'm going to kind of re-explain it in some ways. So far we have used p-values in our hypothesis tests to make decisions about our hypothesis. The significance level gives us a threshold for rejecting the null hypothesis. We can consider a threshold for the test statistic in a similar way. In a chi-square goodness fit test with a significance level, the critical value of the test is the value that the statistic test chi-squared calc that yields p-value equal to the significance level. The critical value is denoted as chi-square crit. The critical value chi-square crit is shown in the diagram. So here is our chi-square crit value. And then you'll see that our p-value and our significance level are actually the same value. So any value that the chi-square crit, any value of chi-square calc that is greater than chi-square crit will yield a smaller p-value. Since the p-value of chi-square crit is the significance level, any value of chi-square calc, so what we've been finding in our calculator, if it's greater than or equal to the chi-square crit value, results in the null hypothesis being rejected. So below, you see this giant table. This is a very nice table that shows you the crit values to do this particular test, right? They are not something you ever have to calculate. They are provided in this table. You may use this table. You could also Google this table as well and find this information. It is not something you're meant to calculate at all. Please do not do it. So in a chi-squared goodness fit test with a critical value of blank, the null hypothesis should be rejected if the chi-square crit value that we get from using our calculator is greater than or equal to chi-square crit. This is called this inequality is called a rejection inequality. So the critical value depends on the degrees of freedom and the significance level of the test. Hence this table having significance levels and degrees of freedom. The table below, it just explains that. So the idea is, instead of going ahead and using the p-value, to figure out is it less than the significance level, instead you're taking that value you get from the calculator, the chi-square calc value, and comparing it to the chi-square crit value that you get from the table. Everything else is still the same. You could do either one. It's an optional thing. One is not necessarily better than the other in any way. It's just an alternative. So this is the step-by-steps and how you would use this. Once again, you'd make your null and alternative hypothesis. you would state your significance level, you would go ahead and find your chi-square value. Once again, you would use your calculator to do that. Then you would find your crit value from your table. So once again, you're getting this from your table. And then you're going ahead and comparing it. And then you're going to determine if you're going to accept or reject that null hypothesis. And that's how you can use critical values to do a goodness fit test instead. Okay, when you're looking on eCampus, there is an assignment that goes along with this. It's on the other paper that I gave you, page 399 through 401, 1 through 3. You'll also see on campus an optional assignment called crit values that lets you practice this method instead. That is an optional assignment. It might show up on your test. I don't know. I haven't really made the test, so I can't tell you that yet. But once again, for the purpose of your IA and for the purpose of your IB exam, it is something you should know. So whether you choose to do that assignment or not is up to you. I am not going to grade it. I am not going to check it. But you need to have some personal motivation to be successful. So do what you need to do. Make sure you get your assignment done and turn in to me when I see you next.